Let us now go straight away to audience questions, and I will simply read these off and ask whoever wishes to speak to them to give me a sign. There may be some where you both wish to say something. So starting out with, how do you seal the cryocompressed hydrogen? Is there sealing and valve which can handle 350 bar and 30 Kelvin at the same time?
Yes, there was already. At the time at BMW, there was a cryogenic compressed valve being developed, and now we need to redimension that. We're currently doing that, and we're hearing from the valve designers and based on our internal investigations that this is very doable.
Daimler before, Christian, did you want to add anything?
That was quite complete, so no.
Okay, thank you. Just give me a sign if we'll start with one of you and then the other one can give me a sign if they wish to. Okay. Here's the next question. You are communicating about 20 to 50 watt. Daimler before presented heat losses for the subcooled liquid hydrogen tanks at 5 watt. Do you expect you could reach 5, or is this unrealistic?
I think it is just not necessary. That's the simple answer. We don't need it. If you look at the dormancy times, we don't need it. It's a huge advantage that we can simplify insulation. If we want to simplify insulation, we want to have a prefabricated insulation that can be produced anywhere, being delivered to us, and we just automatically deploy it. So we actually believe that we do not need 5 watts, and we will not even try to reach 5 watts. We will work with something in between 20 and 50 watts.
Thank you very much. Tobias told us a little bit earlier that this is essentially proven up, that the technical readiness level has been established. We do have a question, though, from the audience. What is the technical readiness level on the cryocompressed tank?
If you look at the passenger car side, it was TRL 7 that was reached in 2012. So there has been vehicles deployed. There have been public dispenser being tested. There has been winter and summer testing in the cars. So I guess TRL 7 is fair. We think that we can reach TRL 7 or even 8 within the next 2.5 years for the truck system.
Thank you very much. Next question. And all of these, by the way, have lots of likes. We have lots of audience members who are contributing either thumbs up or questions. Has crash assessment been performed? What's the effect due to tank failure?
Yes, crash assessment has been done at BMW at the time, and I think that was even a very exhaustive testing. All kinds of passenger car crashes have been performed at the time. For trucks, I have learned myself that truck crash testing is very different from passenger cars, and we have lower requirements here. We have no indication that we should fear any crash because we have a dual shell system. So basically, we have an insulating system, and we have a very, very stiff internal carbon fiber overwrapped aluminum vessel here. It's a Type 3 vessel. So crash is certainly not a risk, but an opportunity for such a system. It can absorb some energy and still would be stiff enough not to leak.
And also to you, Tobias Brunner, you mentioned compatibility with infrastructure. Here's a question from the audience that reads, are there synergies between pipeline transport of hydrogen and your technology?
We heard in the initial presentation from LBST, there always is, because you can combine liquefaction with pipeline systems. So you can basically liquefy here in Germany and then transport liquid hydrogen to the stations. However, you could definitely run such a system from a compressed gas station, so with a pipeline supply or even trailer truck in. Just the density would be lower, the efficiency would be lower. But we expect that we could still stay at a 35 MPa maximum pressure at any station, and we could use that opportunity to fuel long-haul trucks. So that's a massive synergy. Yes, we think so. We still believe that the liquid hydrogen pathway is the more relevant in the future because liquid hydrogen will be cheap. It will be extremely low carbon footprint. So that's a huge opportunity. We are fully aligned with Daimler that this is the perspective of the future.
Thank you very much. Moving on to the next one. If carbon fiber is going to be used for 35 MPa, won't there be a problem for maintaining the vacuum level of the tank?
That's a good question. Basically, yes, there is a risk of outgassing. However, we will not run this system in a temperature range than it was necessary for a passenger car. We stay cold all the time. So the assumption is that basically we have very, very few maintenance events where the carbon fiber would see any ambient temperature. So basically it is cryogenic all the time. And then we have some measures to prevent outgassing, which we cannot disclose today. And finally, we believe we can accept a high heat leak into that system. As I said, it could be a factor 4 or even 6 of that of a liquid hydrogen storage. So we are pretty confident that we can handle this.
Thank you very much. And here is an audience question asking, which of the truck OEMs will use the cryocompressed hydrogen technology? You're allowed to be optimistic on this one.
We actually are working with truck manufacturers, but we cannot disclose with whom today. Please expect that within the coming 3 to 6 months, there will be multiple announcement of our corporations within the next 3 to 6 months.
Thank you very much. Next question, can you refuel the cryocompressed hydrogen tanks at a normal 350 bar hydrogen refueling station as well as in a dedicated cryogenic HRS?
Basically, we could define a scheme to use existing ambient temperature gaseous 35 MPa stations. Yes, basically that is possible. However, that is not what we advise. Some modification would be mandatory because we cannot fill it with 430 bar or something. There is a limit where we went at 35 MPa. So basically, we expect that dedicated stations, at least with a cryocooler on site, would be the more likely solution, and that's what we prepare for. We want to keep this storage running at cryogenic temperatures all the time, which is good for fatigue, good for durability, and good for insulation stability.
Thank you very much. And moving straight down the list, we have heard from Toyota that for gaseous hydrogen, up to 5,000 refueling cycles are possible. Are the 2,000 cycles in cryocompressed too low?
I don't think so. That's more than 1 million kilometers in a truck. We have a much higher capacity. We talk about systems with 80 kilograms or more. So we don't need so many refuelings. We distribute over multiple vessels, as they do too, but basically we have a higher capacity, so we don't need these refuelings. However, if there is more needed than the 2,000 refueling cycles, we're quite confident that we even can do that.
Thank you very much. And another question, how heavy, kilograms in total, is a storage of 150 kilograms of hydrogen?
That's a good question. I just calculate quickly in my head. It would be something like a ton.
Okay.
1 ton.
Thank you. Is there a special hydrogen refueling? This actually overlaps with the question we had before. I'll just pose it anyway. Is there a special hydrogen refueling station needed for cryocompressed hydrogen? Are there existing technologies available, or is it necessary to develop a new fueling technology?
Some new refueling technology needs to be developed in any case. That's true for SLH2, and it would be true for cryocompressed hydrogen. However, cryocompressed pumps are available at some stations today. Here in Munich, we have, I think, 5 stations with a Linde cryopump. That is a small cryopump that we would need to see some retrofitting, but we believe that that we will have a station by 2023 and that works based on liquid cryopump and maybe some boosting devices that we cannot tell much about today. Also, we believe we can install the first station with a cryocooler into an existing 35 MPa station by that time.
Thank you very much. And another question addressing the vacuum level, so a bit of overlap with what we had before. Are the tanks vacuum insulated? What kind of safety features are implemented in order to deal with standard cryogenic failure modes?
There is everything you know from any liquid or cryogenic compressed hydrogen storage in the past. So there have been safety analysis. You have multiple levels of safety release devices. You have two safety release valves at different pressure levels. You have a burst disc around the vacuum. That's the normal things you have. And I think this at some point in time will also be subject to standardization.
Next question. Why does the compressed, the cryocompressed tank, we've just lost it. Basically, it was this. Why does your cryocompressed tank store less than Daimler's? I think it was 40 as opposed to 44.
Well, we are not having the same vessel geometries, to be honest. So their vessels are quite a bit larger, so we don't have the same dimensions. That's why, basically. Also, we truly have some carbon fiber overlap, so the wall thicknesses are slightly higher potentially. We don't need so much insulation space, so we can compensate for some. But I guess actually the systems that, at least as far as we can compare, are quite close if we have the same package space. We just think one of the advantages of our system is you can package in various manners. You're very flexible with packaging. You can even do everything behind the cabin, or you can distribute vessels over the truck wherever we have an opportunity, and that, we believe, gives us a certain flexibility, so we don't need too huge a vessel at the left and the right.
And here, a hands-on question. Is there a test facility where one can try cryocompressed hydrogen?
There is and there will be. You need to come to nice Bavaria.
That's not too much of an ask. Let me ask both of you to address one last question. Christian Forstner has been sitting here so patiently that I'll let you start us off, and then we'll go to Tobias for the last word. And it's this. It's a question we have heard posed to several speakers in this workshop. What are the synergies between subcooled liquid hydrogen, cryocompressed hydrogen, and 70-bar refueling from your perspective? Christian?
Well, for SLH2 and cryocompressed, it's definitely the supply chain in liquid form that we use both. For 700 bar, 70 megapascal, well, it's the other chain, the gases supply, where we can use our cryocooler also to come up with a reasonable density for our system. So basically, there might not be too much synergies over all three solutions at the same time.
And Tobias, before you address that question, there was one last one that came in just as I was posing it, and it was a follow-up question to the testing one. And the question was, who's going to provide the trucks for that test? This may be a trick question.
It is a trick question. We will disclose it in the coming 3 to 6 months. There will be a truck, I promise.
I thought so. So please, your thoughts on those synergies, if you would.
Yes, I think we offer quite a flexibility. So as we've shown in this presentation, we would have a synergy with any liquid hydrogen supply chain. Basically, it's just a different pump. It's a higher pressure pump, and maybe we have some boosters here that we would include into a station to avoid that we have two large pumps required. So basically, any liquid pathway gives us significant synergies. We both SLH2 as well as CCH2 target a single flow non-com refueling that would give us some synergy also in the upcoming standardization process. Concerning gaseous pathways, as I said, it is not a preferred pathway if you want, because the densities would be lower, and certainly we need some energy for pre-cooling at the station. But as a bridge into a world that has gas and liquid, we regard the combined gaseous 35 MPa plus cryogas station as a very interesting opportunity.
Thank you very, very much to both of you, Tobias Brunner, Christian Forstner from Cryomotive, for this very intense and very, very interesting presentation. And again, we wish you utmost success with your further endeavors.